Okay, hello, welcome back. So, as we are continuing our journey in the world of work and energy, there is an important class of systems and situations in which the energy of the system remains conserved. And we want to study those conditions. But before we can tackle this problem, we need a few tools in our toolbox. The first thing we need to study is the concept of conservative forces. And as you can guess by the name, these are the class of forces that are related to energy being conserved. So let's go and define these. Define a conservative force. Let me write it. Conservative force is one whose work does not depend on the path. Does not depend on the path. In other words, amount of work only depends on initial and final locations. Initial and final locations. So if a force has this property, we call that conservative force. We will see quickly why, but let me give you some examples. So examples of, maybe it's easier to start with a non-conservative force. Non-conservative. And imagine on a 2D plane, I'm looking from the top, for instance. I have a box and I move the box around on a path, on a circular path. So as I move this around, I go this way. There is always this resistive friction in the opposite direction of what? Yes, that's good. There is this friction force that resists the motion. And because the force is moving over a distance, it does some work and it happens to be negative. If I take a longer path, the amount of the force, let's assume, remains constant, but I traverse a longer distance, so I do more work while I go back to the same location. So the amount of work depends on the path, the length of the path, and because of that, friction is a non-conservative force. Equivalently, the actual force that is pushing the box around and moving it along this circular path is also non-conservative, because as I push with this force along a bigger circle, the amount of work I do is bigger, and not just depending on where I start and where I end. So both a friction force and, let me write it down. Friction force is a non-conservative force. Usually this externally applied forces, unless they follow specific rules and you have a certain way of defining or applying the force. In general, these external forces are also non-conservative. What are the examples of... Ooh, that's not good. Examples of conservative conservative forces. Non-conservative forces. A good example is gravity. You saw as we go from some initial height to some final height, the work of gravity, let's do it this way. The work of gravity was minus mg y2 minus y1. Doesn't matter what path you take, you may even go up and come back down. It only depends on initial and final positions of the object relative to, well, in vertical direction. So that because of that, it fits the definition. This is a conservative force. Another one is a spring force. That again, you saw the work of a spring is 1/2 k L2 squared minus L1 squared. And again, it only depends on the length, at least in the radial direction. And doesn't matter if you stretch it then compress, or compress then stretch, or anything in between. The work remains constant. And this also is a conservative force. So long story short, conservative force is the one whose work does not depend on the path and only on locations. So that is that. We will see soon why this force is relevant and important. So until next videos.